In this lecture, we shall study AVL trees, which is an example of a balanced search tree. Recall that in the previous lecture, we studied implementations of the set data type, which maintains a set of elements and supports the operations search, insert, and delete. We saw two implementations, one which was to store the elements as a list, and the other which was to store the elements as a binary search tree. The list implementation was considered inefficient because each search takes time proportional to the length of the list, in other words, the number of elements in the set. So, n operations can take up to order n squared time. On the other hand, the binary search tree data structure supports insert, search, and delete in time proportional to the height of the tree. But in general, a tree might not be balanced. For instance, inserting elements in ascending or descending order results in highly skewed trees. Here are two examples. If we consider make tree of 1 to 6, recall that make tree was a function that starts with the nil tree and inserts all these elements in the list one after the other. So make tree of 1 to 6 will create a tree that looks like this. It's skewed to the right. Make tree of 6, 5 dot dot 1 inserts elements in descending order into the tree, and this tree is skewed to the left. It will start with 6. The next element to be inserted is 5, which will go to the left of 6. The next element to be inserted is 4, which will go to the left of 6 and to the left of 5, and so on. So, in general, it is possible that a tree has height as much as the number of elements in the tree. This means that the operations on a binary search tree might take up to order n time for search, insert, and delete. So a sequence of n operations might still take up to order n squared time. So where is the advantage in using a binary search tree? The answer is that we can manage to balance a tree so that it is of small height. This brings us to the concept of a balanced search tree. Ideally, we want that for each node, the left and right subtrees differ in size by at most 1. If we maintain this property, then the height of the tree is guaranteed to be at most log n plus 1, where n is the size of the tree. The proof is as follows. When the size of the tree is 1, the height is also 1, which is the same as log 1 plus 1. When the size of the tree is n greater than 1, then observe that both subtrees are of size at most n by 2. Because if each subtree is of size greater than n by 2, then the tree itself would be of size greater than n. And now, inductively, we can see that the height of each subtree is log n by 2 plus 1, which is the same as log n minus 1 plus 1, which is the same as log n. And therefore, the height of the tree itself, which is 1 plus maximum of the height of the two subtrees, is 1 plus log n. But the trouble is that it is not easy to maintain size balance. What we shall opt to do is to maintain height balance instead. This is maintained as follows. At any node, we maintain the invariant that the left and right subtrees differ in height by at most 1. In the earlier case, the left and right subtrees differed in size by at most 1. But now we will maintain the somewhat easier to maintain property of the left and right subtrees differing in height by at most 1. We maintain this property by using tree rotations, which we will describe later. These trees are called AVL trees, named after the inventors of this data structure, Adelson-Wilsky and Landis. One can prove that if we maintain this property, the height of the tree is order log n, where n is the size of the tree. Here are some examples. On the left, you see a tree that is both height balanced and size balanced. We can check it as follows. The tree is of size 6. There are 3 nodes in the left subtree. There is the root node here, and there are 2 nodes in the right subtree. And you see that the difference in size of left and right subtrees is 1. There are 3 nodes in the left subtree. There are 2 nodes in the right subtree. If you look at the left subtree, the difference in size of the left and right subtrees of this tree is 0, because the left subtree here is just the single node 1, the right subtree is just the single node 3, and they are of the same size. So the left part is size balanced. If you consider the right subtree of the original tree, it is this tree, 5 with a right child 6 and with no left child. Here you see that the left subtree is of size 0 and the right subtree is of size 1. So in this tree we maintain size balance throughout. It is also true that height balance is maintained, because on the left, if you take the overall tree, the left subtree is of height 2 and the right subtree is of height 2. If you take this tree, the left subtree is of height 1 and the right subtree is also of height 1. If you take this subtree, the left subtree is of height 0 and the right subtree is of height 1. So this tree maintains both height balance and size balance. The tree on the right is height balanced, but it is however not size balanced. If you take the overall tree, the height of the left subtree is 2, because there is one node here and it has 2 children. The height of the right subtree is 1. So the difference is 1. If you consider this subtree, there are no children, so it is trivially height balanced. If you consider this subtree, it is also height balanced because the height of the left subtree is 1 and the height of this subtree is 1. So both the left and right subtrees of this tree are height balanced. But it is not size balanced, because the left subtree has 3 nodes and the right subtree has only 1 node. Before we move on to the implementation of a height balanced tree, let us look at the bounds. We claim that for a height balanced tree of size n, the height is at most twice log n. The proof is as follows. Let h be the size of the smallest height balanced tree of height h. We claim that for h greater than or equal to 1, s of h is greater than or equal to 2 to the h by 2. S of 1 equals 1, which is 2 to the 1 by 2. Here we take 1 by 2 to be 0. S of 2 equals 2, which is 2 to the 2 by 2. S of 2 equals 2 because the smallest height balanced tree of height 2 that we can create is a node and one child. So it's the 2 node tree. In general, if a tree has height h, then one of its subtrees is of height exactly h minus 1 and the other has height at least h minus 2. Now, the height of a tree is defined to be 1 plus max of the height of the 2 subtrees. So, one of the subtrees definitely has to have height exactly h minus 1 and the other subtree cannot have height smaller than h minus 2 because that would violate the height balance property. Now, sh in general is 1 plus sh minus 1 plus sh minus 2, which is greater than or equal to, this is a loose bound, sh minus 2 plus sh minus 2, which by induction hypothesis is 2 to the h minus 2 by 2 plus 2 to the h minus 2 by 2. This is nothing but twice 2 to the h minus 2 by 2, which is 2 to the h minus 2 by 2 plus 1. This simplifies to h by 2. So overall we have s of h is greater than or equal to 2 to the h by 2. Therefore, a height balanced tree with n nodes has height at most twice log n. Having established the mathematical bounds, let us look at how to implement a height balanced tree. If you recall, we mentioned that we maintain height balance by using tree rotations. No, there are two types of tree rotations, rotate right and rotate left. Rotate right is defined as follows. We have a tree with root x and left subtree with its own root y and subtrees t1 and t2. The right subtree of the bigger tree is t3. Now we rotate this to the right, by which we mean that we will push this y up to the root and pull the x down. By pulling the x down, we mean that we will make x the right child of y. But if so, what do we do with the original right child of y? We make that the left child of x. Recall that y was earlier the left child of x, but now once we pull x down, x does not have a left child, so we can make t2 the left child of x. In doing this, we still maintain the binary search tree property. Notice that every node in t1 is smaller than y. Every node in t1 is smaller than y. t1 appears to the left of y. Y appeared to the left of x. Y is smaller than x. But now x appears to the right of y. And clearly y is smaller than x. Or in other words, x is greater than y. Every node in t2 appears to the right of y. So it's greater than y. But on the other hand, it appears in the left subtree rooted at x, so it is smaller than x. If you look at the new configuration, t2 appears to the left of x, so every node in t2 is smaller than x, but t2 is part of the right subtree of y, therefore every node in t2 is greater than y. So the search tree property, if it was maintained earlier, it would also be maintained after the rotate. This operation is useful when t1 has large height. As you can see, now earlier the subtree to the left of x had height 1 plus height of t1. Now the left subtree of the root has only height t1. So in this manner, we can reduce the height of the left subtree of the overall tree. The rotate right operation can be implemented in Haskell as follows. Rotate right of node t1 y t2. We just state this pattern here. X, which is the root, t3, which is the right subtree, equals, we just write the pattern for this tree. Node t1, which is the left subtree, y, which is the root, and node t2 x t3, which is the right subtree. The symmetric operation is rotate left, where the original tree has root y and right child x with its own subtrees t2 and t3. The left child of the original tree is t1. Now, in case t3 has large height, we might want to push t3 up towards the root of the tree, which is what we are doing. We are achieving this by pushing x towards the root of the tree and pulling y down. So when we push x to the root of the tree and pull y down, y becomes the left child of x. The previous left child of x, namely the subtree t2, now becomes the right child of y. Because now earlier the right child of y was x, now the right child of y has been freed up. So we can let t2 occupy that position. Again, we can check that if the original tree satisfies the search tree property, after the rotate left also, the tree will continue to satisfy the search tree property. This operation is useful when t3 has a large height, and it is exactly the inverse of rotate right. And the Haskell description is again very simple. Rotate left of this pattern, which is specified by node t1 y, node t2 x t3, equals node of left subtree, which is node t1 y t2, x, which is the root, and t3, which is the right subtree. Having seen the operations rotate right and rotate left, we will now see how to use those two operations. Assume that the tree is currently balanced. Each insert or delete operation performed on the tree might create an imbalance. What we do is to fix the imbalance using a rebalance function which involves rotate rights and rotate lefts. Before we actually describe the rebalance function, we will take care of some preliminaries. We need to compute height of a tree and its subtrees to check for imbalance. Recall that we are implementing a height balanced tree, and imbalance means that we have a node such that one subtree and the other subtree differ in height by at least 2. So we need to compute the height of a tree and its subtrees to check for imbalance. Usually height would be defined as follows: height of nil equals 0, height of node TL x tr equals 1 plus max height TL and height tr. But unfortunately, this definition takes order n time to compute height. And we would not like to spend order n time for performing an operation which would be performed multiple times during each insert and delete. We can save this effort by storing the height at each node. So the new structure is as follows: data AVL tree A equals nil or node AVL tree A, which stands for the left subtree, A, which stands for the value at the node, int, which stands for the height, AVL tree A, which stands for the right subtree. Now the height function is a constant time operation which is defined as follows: height nil equals 0, height node TL x h tr equals h. We also need a measure of how skewed a tree is, namely its slope, and we define it as follows: slope of nil is 0, slope of node TL x h tr is nothing but height of TL minus height of tr. We use this to determine whether a tree is still balanced or not. If slope is greater than or equal to 2, then or greater than or less than or equal to minus 2, then we know that the tree has an imbalance. Let us now give implementations of rotate right and rotate left with the new data declaration. The wrinkle is that since we store the height at each node, every time we touch the tree, we need to adjust the height. Here is the definition of rotate right. Rotate right of node TLL Y HL TLR. TLL is the left subtree of the left subtree. TLR is the right subtree of the left subtree. HL is the height of the left subtree. X, which is the root. H, which is the height of the tree itself. And TR, which is the right subtree of the original tree. Equals node TLL Y NH node TLR X NHR TR. This definition is exactly the same as the definition earlier, except that we need to recompute the heights. NH is the new height of the overall tree, and NHR is the new height of the right subtree. NHR clearly is 1 plus max of height TLR and height TR. NH is 1 plus max of height TLL and NHR, because for the overall tree, NHR is the height of the right subtree and height of TLL is the height of the left subtree. Clearly this is a constant time operation because we modify one pattern to another pattern, and in computing the new heights we are just comparing a constant number of heights against each other. Here is the symmetric definition for rotate left. We just repeat the earlier definition with the appropriate heights inserted, and in the result we have the new heights NHL and NH, where again NHL is defined as 1 plus max height of TL, height of TRL. NH is defined as 1 plus max of NHL and height of TRR. This is again a constant time operation. Having looked at the rotates, let us now consider how to rebalance trees. This is the most crucial function in the implementation of AVL trees. Recall that slope of a tree is the height of the left subtree minus height of the right subtree. In a height balanced tree, slope is -1 or 0 or 1. But after an insert or delete, it can happen that the slope is -2 or +2. A slope of -2 or +2 constitutes a violation. It cannot be less than -2 or greater than +2 because we are just inserting one node or deleting one node. Now, the violations can happen only at nodes that are visited by an operation. Recall that to insert or delete, we need to start at the root and search for the node that we need to insert or delete, and in doing so, we will be traversing a path from root to that node. Only those nodes along the path will be affected. So, what we need to do is to rebalance each node on the path visited by the operation. There are many cases to consider. Let us first consider the case where the slope is +2, which means that the height of the left subtree is exactly 2 more than the height of the right subtree. The case where slope is -2 is symmetrical to this, and we will not be elaborating that. So let us assume that the slope of a tree is +2 and both subtrees are balanced. Here, two cases might arise. Let us look at the first case. The first case is when slope of left subtree is 0 or 1. Here is the scenario. We have a root x whose left child is y, which is the root of a tree consisting of y, t1 and t2. Now we said that the slope of the overall tree is 2, therefore the height of the tree rooted at y is h plus 2 and the height of t3 is h. If the height of the tree rooted at y is h plus 2, it means that one of the children is of height h plus 1 and the other child is of height h or h plus 1. Since we say that the slope of the left subtree is 0 or 1, therefore it has to be the case that the height of t1 is at least as much as the height of t2. If the height of t1 were smaller than the height of t2, then the slope of the tree rooted at y would actually be -1. Since we say that the slope of the left subtree is 0 or 1, it has to be the case that t1 is of height h plus 1 and t2 is of height either h or h plus 1. This is the scenario, in which case all we need to do is rotate right. This brings y up to the root, it brings x down to be the right child of y, and it shifts t2 from being the right child of y to the left child of x. Everything else is unchanged. Let us look at the slopes of the various subtrees before and after the operation. Earlier the slope of x was 2 and the slope of the left subtree was 0 or 1. Now the slope of the new tree is height of left subtree, which is h plus 1, minus height of the right subtree, which is either 1 plus h or 1 plus h plus 1. So the height of the right subtree is either h plus 1 or h plus 2. So in doing this rotate right, we have managed to bring the slope from 2 to either 0 or -1. This is for the root node. For the right subtree, the slope is just +1. So the new tree that we get is height balanced. Here is the next case. This is the case when the slope of the tree is 2 and both subtrees are balanced, but the slope of the left subtree is -1. So the tree looks as follows. We have the root x whose left child is y. which has subtrees T1 and T2, but we have expanded T2 into its root Z on the two subtrees T21 and T22. The right subtree of X is T3. Since the slope of the tree is 2, the height of the left subtree rooted at Y is H plus 2 and the height of T3 is H. But the slope of the left subtree is minus 1, which means that the height of T1 is H and the height of the subtree rooted at Z is H plus 1. For the height of the subtree rooted at Z to be H plus 1, it has to be the case that either T21 or T22 is of height H and the other is of height H minus 1. So this is the scenario. Now we achieve a height balanced tree in two steps. In the first step, we rotate left at Y. So what happens is that we just concentrate on the left subtree of the original tree, this portion, and we rotate left at Y, which means that we pull Z up, we push Y down. That's what we have done. But when you pull Z up and push Y down, you make Y the left child of Z, which means that T21 needs a place to go and it goes as the right subtree of Y, which is what happens here. You have T1, which was the original left subtree of Y, still being the left subtree of Y, but you have T21, which was originally to the left of Z, now to the right of Y. Z has moved up and become the parent of Y, and T22 is, as before, the right subtree of the tree rooted at Z. We have only changed this portion. Now, what we have achieved is to balance the subtree rooted at Y. If you consider the subtree rooted at Y, the slope is either 1 or 0. But the subtree rooted at Z might have an imbalance. And the imbalance will occur in case T22 is of height H minus 1. Because the left subtree rooted at Y now has height H plus 1, because T1 is of height H. But the right subtree has height only, if the right subtree has height only H minus 1, then there will be an imbalance at Z, and this imbalance would be caused by its slope being 2. To fix this situation, we do a simple trick, which is to do a rotate right at X. If you do a rotate right at X, what happens is that X goes down as the right child of Z, Z becomes the new root, T22 becomes the left child of X. This is the situation. We have Z as the root, Y as the left child of Z, and T1 and T21 being the subtrees of the tree rooted at Y as before, as here. But we have done a rotate right at X. So Z is the root, X is the right child, and T22 and T3 are children or subtrees of the tree rooted at X. Now let's compute the various heights. Height of T1 hasn't changed yet. Height of T21 is either H or H minus 1. Height of T22 is either H or H minus 1. T3 is of height H. Now, height of the subtree rooted at Y is H plus 1, and height of the subtree rooted at X is also H plus 1. So, we have got a tree whose slope is 0 and balance has been restored. Rebalancing for the case when slope equals minus 2 is symmetric to the slope equals 2 case. We have two subcases, one where the slope of the right subtree of the root is either 0 or minus 1, and one where the slope of the right subtree is 1. And the cases are handled symmetrically. So here is a Haskell implementation of the rebalance function. Rebalance is a function from which takes an input AVL tree A and produces an output of type AVL tree A. Rebalance of node TLXHTR is in the case where the absolute value of ST is less than 2, ST is the slope of the tree, slope of node TLXHTR. Just for reference, STL is the slope of the left subtree, TL. STR is the slope of the right subtree, TR. So, in the case where the absolute value of ST is less than 2, which means that ST is either minus 1 or 0 or 1, then you just return the tree as it is. In case when ST is equal to 2 and STL is not equal to minus 1, which means that STL is either 0 or 1, this is the first subcase we looked at, then you just do a rotate right at the root x. In case the slope is 2 and the slope of the left subtree is minus 1, then you first do a rotate left of the left subtree and then you do a rotate right of the overall tree. And the cases for the slope being minus 2 are symmetric. If the slope of the tree is minus 2 and the slope of the right subtree is not equal to 1, then you do a rotate left at the root. If the slope is minus 2 and the slope of the right subtree is plus 1, then you first do a rotate right of the right subtree and then do a rotate left at the root. It is left as an exercise for the reader to work out the symmetric cases and ensure themselves of the correctness. Notice that rebalance is a constant time operation because we just do either a rotate right or a rotate left or a rotate right and a rotate left. Recall that rotate left and rotate right are themselves constant time operations, and apart from this we just compute the slope, which is again a constant time operation. Now let us consider the key functions on an AVL tree, namely search, insert and delete. Search is as usual. Search of nil v is false. Search of node TLXHTR, we are searching for a value v in a tree given by this pattern. If x is the same as v, then you return true. If v is smaller than x, then you have to descend down the left subtree. So you do a search TLV. Otherwise, you do a search TRV. And the time taken is proportional to the height of the tree. But now we have proved that in a height balanced tree, the height is twice log n, where n is the size of the tree. So therefore, search takes order log n time. More important is insert and delete. Here we see how to use rebalance. Insert is a function which has the signature order A implies AVL tree A, arrow AVL tree A. This is the input tree. This is the value to be inserted. That is the output tree. Insert V in the nil tree is nothing but node nil V1 nil. Notice that we enter the height of the tree when we create the single node tree. Insert node TLXHTRV is as usual. If x is equal to v, then you don't need to do anything, so you return the tree itself. If v is smaller than x, then we have to insert v in the left subtree. So we do a rebalance after we insert v into the left subtree. So we do rebalance of node NTL x NHL TR, where NTL is insert TLV. NHL is the new height of the left subtree, which we calculate by 1 plus max of height NTL height TR. Otherwise, this is the case when v is greater than x. In this case, we have to insert v in the right subtree. So we insert v in the right subtree and get NHR, NTR. NTR is insert of TRV. NHR is 1 plus max height TL height NTR. And then we do a rebalance. Again, the time taken is proportional to height, and we do a rebalance at each node that is touched on the way to insert. But rebalance is a constant time operation and height is proportional to log n. So therefore insert again is an operation that takes time proportional to log n. Here is delete. Delete nil v is just nil. Delete v from a tree of the form node tl x h tr. Again, we consider three cases. If v is smaller than x, then we delete v from the left subtree and get ntl. ntl is delete tlv. The new height of the left subtree is nhl, which is computed as usual, 1 plus max height ntl height tr, and we take this tree and rebalance it. In the case where v is greater than x, we delete v from the right subtree and we rebalance the overall tree. The crucial case is when v is equal to x, in which case we do deletion as in the binary search tree case. We first check if the left subtree is nil. If that is the case, then we just replace the tree node tlxhtr by just tr, because we are deleting x and there is no left subtree of x, so tl is nil, and tr is the right subtree of x. Tr can take the place of x. So this is what we return. Otherwise, we consider the maximum element of the left subtree, which is y, which is gotten by delete max of tl. This delete max is exactly as we saw earlier, and ty is the left subtree after the maximum element has been deleted, and we just replace the node x by y here, and tl is replaced by ty, and hyr is the new height, and we rebalance this tree. Again, the time taken by this operation is proportional to height, which is 2 log n, assuming delete max behaves well. But delete max does indeed behave well, and the implementation is just like earlier. Modulo adjusting the heights. Again, time taken is proportional to twice log n. In summary, we have defined AVL trees which supports a set data structure supporting the operations insert, delete and search, each of which take order log n time, where n is the size of the set. Therefore, a sequence of n operations takes order n log n time. This is a fundamental but non-trivial data structure and is an excellent example of the power of Haskell. As you may have seen during the course of this extended example, the mathematical definitions pertaining to height balanced trees could be transcribed almost directly to Haskell code.